Venkatesh Raman sir, am I audible?
Yes, I can hear you. Can you hear me? Can you hear me?
Sir, can you hear me?
Yes, I can hear you. நான் பேசுறது கேக்குதா? Hello.
Sir, can you hear me, sir?
I can hear you.
Yes, yes, sir.
But நான் பேசுறது கேட்கல போல இருக்கு.
Sir?
நான் பேசுறது உங்களுக்கு கேட்கல.
Sir, clear கேக்குது sir.
அப்ப அதிலே சொல்லலையே, நான் எவ்வளவு நேரம் சொல்லிட்டு இருக்கேன்.
Now only here, sir.
Okay, fine. Yeah, I can hear you. நான் சொல்லிட்டு இருந்தேன் actually.
Okay, sir. Okay, sir.
Screen share பண்ணி check பண்ணுங்க.
Good evening to each one of you present here. Here we are at National Conference on Contemporary Mathematics and Applications. It's a great pleasure for me to introduce our keynote speaker in the session, who is going to talk to us about the topic, some maths in tournaments. On behalf of PG and Research Department of Mathematics, I am pleased to welcome our speaker, Dr. Venkatesh Raman, Professor, the Institute of Medical Sciences, Chennai. He completed his MSc Mathematics at Kanpur, Master of Mathematics in Combinatorics and Optimization at University of Waterloo, Canada. He pursued a PhD in Computer Science at University of Waterloo, Canada. His area of interest are parametrized complexity, exact exponential algorithms, data structures, sorting, selection and searching, approximation and randomized algorithms. He has more than 3 decades of experience. He has published and presented more than 80 articles in refereed journals. He visited various universities as a visiting professor and also visiting scientist, such as University of Waterloo, Canada, Max Planck Institute of Informatics, Germany, Royal Holloway University, UK, University of Bergen, Norway, and many more. He has supervised 5 PhD students and many more PG students. Other than that, he also a member of numerous committees like IWPEC Steering Committee, a DST, DAD, Indo-German, and Council of Indian Association of Research in Computing Science, etc. Once again, I warmly welcome you, sir, to take a part of this session. Thank you.
Okay, thank you. Can I share my screen?
Yes, sir.
Okay. Is my screen visible?
Yes, sir.
Okay, good. Thank you. Thank you very much for the introduction, and I thank the organizers for inviting me. So since it's late in the day, I'm just going to walk you through very gently and hopefully make it interactive. What I'm going to do, rather than talk about some hi-fi research, I'm going to just generate a lot of interesting questions through how you form, design fixture for tournaments or points in the tournament table and so on and so forth. Okay. So I believe you can all access your chat window. So I would make it interactive and I would expect people to answer some of my questions through chat. And it's going to be a very light talk. Okay, so let me start with the first question. So this is, for example, the points table on IPL in April 20th, 2019. Now, I presume all of you understand these columns in the points table. First column says played, won, lost, no result, points, and net run rate. Okay. So now just look at attention, keep paying attention to the first column. See, I can understand that people will get points based on how they win or lose games. But look at the first columns. Some teams have played 3 matches, some have played 4, and some have played 5 matches. Okay, this looks a little unfair that while one team is playing only 3, the other team has already finished 5 matches. Okay, now this is the tournament designer who is doing it, all this, right? So here is another table. Some have played 8 matches, some have played 9 matches. Here is another table. At some point, everybody has played 13 matches. And here some have played 13, some have played 14. So now, here is my question. Can you design a fixture? So you are suppose designing this tournament. Can you design it in a way that everybody synchronizes? At the end of some day, everybody has played 1 match. At the end of some days, everybody has played 2 matches, and so on and so forth. Okay, so you can see my screen, right? And can you see my screen? Can somebody answer? Yes, no? Is my screen visible? Hello?
Yes, sir.
Yes, no, padal solunga.
Yes, sir. Yes, sir.
Okay, that's what I'm waiting.
Yes, sir.
Okay, good. Just want to make sure that people are, there, not sleeping, watching, and so on. So my question now is, can you design a fixture so that at the end of some day, every team has played 1 match. At the end of some day, every team has played 2 matches. Ellarum one synchronize panni, can they play? That is my question. Okay. So you are a tournament designer. Let's assume that there are 4 teams, A, B, C, D, and there is only 1 match every day. And suppose every team plays against every other team twice. Okay. So A plays with B twice, C twice, D twice, like in IPL. So every team plays 6 matches each. Now, what I want to know is, can you design the tournament so that at the end of the first match, first day or some day, everybody has played only 1 match. Then after some number of days, everybody has played exactly 2 matches, and so on and so forth. So is that possible? Yes, no? Can you answer in chat? So there are 4 teams, A, B, C, D. I want you to design the tournament, which means you decide who plays with whom. And I'm asking, can you make sure? Yes, first match between A and B. Yes. Okay. And then? Okay, second match between C and D. So at the end of it, everybody has played 1 match each. Okay, good. Now, idhe madri, you can keep doing it so that at the end of some days, everybody would have played 2 matches each. And then everybody has, so nobody goes forward. Okay, they are all synchronized. Now, suppose I have, now let's change the rules of the game. Suppose there are 5 teams. Can you do the same thing? Can you make sure that everybody has played exactly once? There are 5 teams. You are allowed to design games. And Dr. Vijay Lakshmi says, no, it's not possible. Okay, good. And what about, can you make sure that everybody has played 2 matches each? There are 5 teams. That is possible because think of, A plays with B, B plays with C, C plays with D, D plays with E, E plays with A, then everybody has played 2 matches each. So somehow you can realize that we can't get them all to have played 1 or 3 matches each, but you can make them play 2 matches each. Okay. Now, one can generalize the question. That's all mathematics is all about, right? What if there are n teams and we want each of them to have played exactly k matches each? Okay. Now, what can we say in general? What is the math behind it? How do we even model this problem? Okay. So this is not like a differential equation or complex analysis or topology. How do we model this problem? Well, you can model this problem. Some of you may already seen this. You can model this problem using what is known as graph theory, right? So what is a graph? Well, in high school, you all might have seen this kind of graphs to represent curves. No, this is not the kind of graphs we are looking at. We are looking at the graphs like this, and the graphs are basically points and lines. You have a set of points and you have a set of lines connecting pairs of these points. And these nodes are called vertices. Pairs of them are called edges. Some edges can be directed. Some of them can appear more than once. It's multi-edge. And graphs model electrical networks, social networks, road networks, can model any kind of relations. Okay. Now, in fact, contemporary, this whole conference is about contemporary mathematics. Contemporary mathematics, graphs play a central object. Professor Mike Fellows, who is a famous computer scientist, used to say that, how in classical mathematics, numbers played a big role, right? We talk about rational numbers, real numbers, complex numbers, algebra, field, ring, and everything defined using numbers. In modern mathematics, graphs, this kind of graphs form a very central object. And this graph theory, graph algorithms is a huge, huge area in contemporary mathematics. Okay, so I've defined what is a point, what is a line, what is the degree of a vertex, number of edges incident on a vertex. You can talk about in directed graphs, number of out degree and in degree. So now let's come back to my first question. What is the graph theoretic question I'm asking? Can we make all teams to have played exactly k matches each? What is this question in the graph theory language? In the language of graph theory, how can you phrase this question? Okay. See, much of mathematics is also about modeling real world problems. It's not just enough to give you differential equations to solve. You have to even come up and model it, right? So how do you model this question? Can we make all teams have played k matches each? This is same as asking, is there a graph on n vertices with degree k? So this is a k regular graph. So the question is there a k regular graph on n vertices for any k and any n? Okay. Now, what we saw was that if there are 5 teams, you cannot play in a way that every team has played exactly one match. So yeah, each team must have k degree, exactly. So there are 5 teams. We know that there is no one regular graph on 5 vertices. That is our observation. When we notice that there are 5 teams and you want each one to have played one match each, that is not possible. Okay, so it's the same as saying you cannot have a graph on 5 vertices where each degree 1. Okay, how do we prove this? Okay? It's not enough to say that maybe it doesn't look like you can do it, but how do we prove such a thing? Well, here is the argument. Sum of the degrees of vertices in the graph, maybe some of you have seen it. Can you say what it is in chat? If you have a graph and each vertex has certain degree, if you sum all the degree, what is this number? What do you get? Twice the number of edges, exactly, right? So it's 2 times the number of edges. The important observation is it's an even number, and so you cannot have number of vertices with odd degree is always even. So you cannot have degree 1 vertex, 5 vertices all having degree 1 is not possible. Okay. This is called handshaking lemma, and more or less the first theorem in graph theory you learn. So what is the observation? In the points table picture, so that if there are 5 teams, everybody has played exactly 1 match or everybody has played exactly 3 matches. Okay. In general, there is no graph on n vertices with all vertices having degree k when n and k are odd. Okay. So this is something you can actually teach high school students, really, So my point is to say that graph theory is rich. Instead of teaching in a very abstract way about here is a point and this is some of the degrees, run it through tournament. So this was some observation. I was looking at the points table for several days and I said, why is it that in the points table, you do not have all teams have played exactly the same match some days? Well, if there are even number of teams, it's possible. For all numbers, you can get it. But if there are even odd number of teams and if you want everybody to have played odd number of matches, that's not possible. And here is the argument, because the sum of the degrees is even number. Now, okay, so this tells you that if n and k are odd, you cannot have n vertices with degree k. But what otherwise, it turns out it's always a possible. You can always construct a graph on n vertices and degree k for any n and k as long as one of them is even. This can be a very nice exercise in first course in graph theory. Okay, so my point is to tell you that here is, there are many students out there and many teachers. Here is one way to teach graph theory gently through these kind of tournaments and points table, and it can be appealing. Okay, now let me move on to my next question. Here is a different question. Can the first column have all different numbers? Okay, I proved you, or I discussed with you that if you want everybody to have played 3 matches and there are 5 teams, that's not possible. But other numbers, it is possible. So now the question is, can you have a points table? So let's go back to my points table. Yeah, what I want here is that in the first column, which tells you how many matches everyone has played, I want all the numbers to be different. Somebody must have played 7 matches, somebody 8, somebody 9, somebody 3, somebody 2. Can you design your tournament fixture so that everybody has played different number of matches? Now, this is my second question. Anybody has an answer? Okay, Dr. Vijayalakshmi, quite a few people say no. Okay. Can you unmute and tell me why not? Good. At least 2 of them must have same degree. Yes, this is another interesting theorem in graph theory, which tells you that. So this is my question. Can you design a fixture so that every team has played different? Yes.
Sir, audience cannot talk, sir. They
Oh,
only use
okay.
chat box.
நீங்க unmute பண்ணாதான் பேச முடியுமோ?
Yes, sir.
Okay. Yeah. Okay. Thanks. I understand. So the answer is, if you ask the question, there is a nice little, again, theorem in graph theory that in any simple graph, now I have to tell you what simple means. Any simple graph on n vertices, there will always exist a pair of vertices with the same degree. There is a simple pigeonhole principle argument. However, this is sort of a research question. I don't have an answer. But if I allow multi-graph, which means that if I allow more than one edge between a pair of vertices, which means think of every team is allowed to play 2 matches or 3 matches between them, then is it possible that they all have different numbers? Well, I asked this question. I have some examples that it is possible. There are some small, even with 4 vertices, you can have a multi-graph where the degrees are 1, 2, 3, 4. But in general, has this question been studied? I don't know. So here is an interesting question. Somebody is interested to explore this and let me know if you find out the answers. Okay. So what I'm asking is, if I have a graph on n vertices where it's not a simple graph between a pair of vertices, I allow multiple edges. Now, is it possible that all vertices have different degrees? When is it possible? When is it not possible? It would be a nice question. We know that on a simple graph, it is not possible. So my point again is to tell you that these are some standard theorems. Okay, many of you may already know this. You've done a course or you've taught a course on graph theory. But all I'm pointing out is here is a simple way to explain these theorems through the points table, through the tournament points. Okay, here, let me move on to my next question. It's just now, this is again a very standard question in puzzle, so I won't spend too much time on it. Imagine you are running a knockout tournament. What is a knockout tournament? If somebody loses a game, they're out. Okay, so let's say in your college, you're trying to organize, a badminton tournament with some 16 players, and you want to find the winner at the end of the whole tournament. And it's a knockout tournament. The moment somebody loses, they're out. Question is, how many games do you play in this knockout tournament? Okay. Now, if you think about it, you can pair them up. First round, 8 games will happen. Second round, 4 games. Third round, 2 games. And fourth round, 1 game. If you add them all, this is like 15 matches. Okay. Now, in general, one can ask the question, how many games do you play? If there are some 32 players, 64 players, any power of 2. Power of 2 is convenient to assume. What happens? Okay, this is a nice question. Now, how many rounds if you play matches in parallel, right? If there are 16 matches, you know that there is a quarterfinal, semi-final, final. So it will be 8, 4, 2, 1. So it will be like 4 rounds. In general, if there are 2 power k teams, and if you run this, how many matches in parallel? Now, the third question is a more interesting question, which has, people have studied, there are papers written on them. Typically, when you run a knockout tournament, how do you decide the second best team? Right? Usually, what do we do? The loser of the finals is declared as the second best. But there are examples to show that that is a bad way to do it, because the loser of the finals may be actually worse than half the teams, okay, half the players. So there are, in general, think of it like this. If you have n numbers and I want to find the second maximum number, how many comparisons do I do to find the second best number? This is an algorithmic question. And, I'm not going to give the answer here. I'll let you think about it. Anybody who's interested can send me an email and ask. We can take it further. But these are some interesting questions. Okay. So my point again is to tell you that through this notion of tournaments, forming a tournament from the points table, lots of interesting, great mathematical questions can be asked. And it can, some of them are very simple exercises. Some of them are completely open. One can spend a lot of time trying to explore these questions. The more important thing is they're fun. They make you interesting to explore these questions. Here is another question. Okay. Suppose I tell you the score table. Can you believe the score table? Okay, so suppose there are 5 teams. Each team has played each other exactly once. So it's a complete round robin tournament. Everybody has played everybody else. No tie. Every match has a win or a lose. So if they win, you get 1 point. They lose, they get 0 points. Now suppose I tell you this is the final table. Can you believe it? Anybody? So is this a valid table, right? There are 5 teams. They've all played against each other exactly once. If you win, you get 1 point. If you lose, you don't get any point. And there are no ties. Now somebody tell you that here is 5 teams. A has won 5 matches. B has won 0 matches. C has won 2 matches, and so on and so forth. Is this a valid table? Anybody? No. Okay. At least I got one answer which says no. Two answers. Only the teachers are answering. I don't see answers from students. It's not a, a very complex analysis topology question. Completely simple, trivial question. Good. I got some Shanmati who's saying no. Okay. Can somebody give me a reason? Why this is not a valid table? The 5 teams, everybody plays with each other exactly once. Now I tell you, here is the points table. You don't think it's correct. Why not? Exactly. Nobody can get 5 points. The maximum one can get is 4 because there are only 5 teams. Everybody plays only 4 matches. Okay. So this is a simple question, simple answer. Now, suppose I give you this. What about this? Is this possible? Okay. What about this? 5 teams, everybody played exactly once, no ties. Number of matches is given greater. No, now here it's fine. Right? A has won 4 matches, B has won 0, C has won 3 matches, D has won 3 matches, E has won 0 matches. Can you say whether this table is correct or wrong? Or is this possible? Everybody plays with everybody else and no ties. Is this a valid scorecard? Okay, again, I got one answer saying no. Okay, can you give me a reason, Mohammed Abrar? Why not? You're all mathematics students, right? You have to give me a proof. Remember, I said no ties. Every match is won or lost. C and D cannot have the same points. Why not? That's possible, right? I mean, I really appreciate you answering. Okay, first of all, thank you. Which means that you are one of the few who is thinking. But no, two teams can have same points. What's the problem? But look at B and E. They both got 0. How is that possible, right? Look, I mean, they both played a match against each other. They must have, one of them must have won. Okay. You can have same points, but you can't have 2 zeros. Because I said there are no ties. Cannot have 2 zeros because B and C, when they have played, one of them should have won and got this 1 point. So this is not a valid table. So, you can keep asking this. I put out all these tables. You can come up with easy conditions that the total sum should be 10 because there are totally 10 matches. 5C2 is 10. So total sum should be 10 because there are no ties. Maximum score can be 4. But what are all the conditions? How can we, say something? Now, there is a nice theorem due to Landau in 1953 who said the following, who actually precisely characterized when such a score sequence is valid. A score. So what is the graph theory question here? I give you a directed graph. I don't give you the graph. I give you the out degree sequence, right? I tell you it's a complete directed graph. Everybody plays with everybody else exactly once. But I only tell you the degrees, the out degrees. Given some out degrees, is there a graph? Okay, this is a very standard question Lot of variations have been studied. So this question I'm asking is, given an out degree sequence, when is it valid? It is valid by looking at the sequence. You can say if the sum of any I of them is at least IC2 and the total sum is NC2. If this condition is satisfied, you take any I of them, any two of them, any three of them, any four of them, they should sum to at least IC2 and the total sum must be NC2. If this happens, then such a sequence is valid, which means there is a graph, a directed graph with the degree sequence, which means there is an outcome of these matches where who has won, who has lost, and you can say what is the score sequence. Okay, so it's a very powerful theorem. It has a proof running into 2-3 pages. One direction is easy, the other direction requires a proof. Okay, so again, my point is that there are a lot of these questions looking at the points table from the pictures of the game. One can come up with interesting questions in maths, and some of them have answers, some of them are something you can explore. Okay. In the interest of time, how much time? I spent half an hour. Okay, I'll continue. So now there is an object in directed graphs called tournaments, which is basically you take, unfortunately, I don't have a pad where I can draw pictures. It will be not so nice to talk about a graph talk without pictures, but I wish I had a board to talk about it. So, in a physical talk, I would have drawn a lot of pictures. So you take an undirected graph and orient every edge arbitrarily. What you get is what is called a tournament. This is a very standard object in directed graphs. And it models tournaments where each team plays every other team exactly once. There are no ties. And what the Landau's theorem is about, when is a sequence, an out degree sequence of a tournament. Tournaments have a lot of nice properties. There is a vertex with out degree n-1 in tournaments. They have what is called a directed Hamiltonian path, a path that visits every vertex exactly once. In fact, this is again a simple exercise on induction. Oh, sorry. A vertex, I said tournaments have a vertex with out degree n-1. That is not true in every tournament. It is true in transitive tournaments. What is a transitive tournament? If there is an edge from A to B and there is an edge from B to C, then the edge between A and C must be oriented this way, A to C, and that's called a transitive tournament, and they have a lot of nice properties. But general tournaments, there may not be a vertex with out degree n-1, but you can prove that there is what is called a center vertex, which means you can visit everybody else through a path of length at most 2. Out degree n-1 means there is a direct edge to every vertex, every other vertex. But this says a path of length 2, which means you can visit every other vertex through a path of length at most 2. There is a vertex with out degree at least n-1 by 2. There are, maybe I won't mention, there are some simple, interesting graph theoretic properties on tournaments. There are, some interesting open problems in terms of algorithmic questions. Okay, so what is an algorithm? Well, I presume, many of you may not be in computer science, some of you may be. So, when you learn in high school how to multiply 2 matrices or how to compute the GCD of 2 numbers. Yeah, is there a question? Meera Jasmine has raised her hand. Maybe there's a mistake. Okay, so I'm going to proceed. All of these properties and graphs can also be looked at in the context of algorithms. So algorithms is a huge ocean, central notion in computer science, where you want to write a program, an efficient method to solve certain problems. how efficiently you can solve is the question. So for example, in these tournaments, I said tournaments have a Hamiltonian path, have a center vertex, all that. There are interesting questions about how fast can you find them, right? How much time does it take to find a center vertex? These are very interesting algorithmic questions. Algorithms is another wonderful, nice area in computer science, which has a lot of applications of mathematics. Finally, I'm going to end with another interesting prediction question, which can be again modeled using graph theory. Okay, so let me start with the question. Suppose you have 4 teams. Again, I'm going to use IPL example. Let's say CSK, KKR, RCB, and DC. And now we have a league, sometimes in American baseball league and so on. Every pair of teams play some huge number of, the whole tournament happens over an entire season, okay, 6 months. So everybody plays with everybody else, some 20 matches, 30 matches, so many matches. So here there are a lot of matches, and this is the current score. Okay, there are 4 teams: CSK, KKR, RCB, DC. Their current scores are CSK has 90, KKR has 91, RCB 91, DC 92. The tournament is not over. There are some more matches left. Specifically, what matches are left? There is one match between every pair of them is left, except CSK versus DC. Okay, that match is not, that is over. This is the current score. There are remaining matches, which is between every pair except CSK versus DC. Now, you are all a CSK fan. So you want to know the following question. You are a journalist trying to report, right? If you've been following these IPL tournaments, in the middle of the tournament, there are some few matches left. Then you will want to know, is there a chance it's going to make it to the top? And people will say, if so-and-so loses in this match, and if this team wins this match and that team wins that match, then you have a chance. Okay, so that's the question I'm asking. Can CSK reach the top? Okay, at least with the tie. Okay, I want you to think about and answer me. Okay, this is a question, very simple question, and then I will generalize, talk about how do you model this in graph theory, and end with my another pitch on graph theory. But here is a simple question. This is the current score. CSK has 90, KKR has 91, RCB has 91, and DC has 92. There are some 5 matches left. 5 matches, CSK and KKR, CSK and RCB, that's 2. DC plays with RCB, DC plays with KKR, and DC plays with, and KKR and RCB, they play. There are 5 matches left. So, one match between every pair except CSK versus DC match is left. Given that, can somebody tell me that is there any scope for CSK to reach the top even with the tie? Okay, let me ask a simpler question. What is the maximum point CSK can get? Again, no ties, win or lose. If you win, you get 1 point. If you lose, you don't get any point. What is the maximum score CSK can get? I've told you the current score. I've told you what are the remaining matches. What is the maximum score CSK can get? Can somebody say in chat? Four teams. I'm going to repeat. I'm not going to proceed until I get some answer. I'm willing to repeat 5 times if you want, but because it's not a difficult question. There are 4 teams. I want you to get into the game, into the math, right? So there are 4 teams. Their current scores I have written: CSK has 90, KKR has 91, RCB 91, DC 92, and there is 5 matches left. Between every pair, there is one match left except CSK versus DC. So what is the maximum score CSK can get? I will wait. I'll wait for 1 hour until I get an answer. I'm not going to proceed. Because this is my 5th standard question. It's not a BSc question. Okay, Dr. Sivagami says CSK can get 494. Okay, first of all, let's see how many matches are left for. I mean, students should answer. I really want students to answer. How many matches are left for CSK? கிளாஸ்ல பேசியே இந்த மாதிரி இன்ட்ராக்ஷனே பழக்கம் இல்லாம போச்சு. இட்ஸ் ஆல் ஒன் டைரக்ஷன். somebody will flash the slides அப்படியே கேட்டு ஏதோ சினிமா பார்க்குற மாதிரி பார்த்துட்டு இருக்கோம். How many matches are left? I mean, if you don't answer this, I am not going to proceed because I don't see any point in me continuing with the talk if you don't answer this question. How many matches are left? You can ask me questions, sir, puriyave illa, can you tell me again? Feel free. At least somebody should ask me that. I don't understand. Please repeat. I am willing to repeat. Okay. But you have to answer this question. I have written 2 sentences in the slide. Based on that, I am asking a question. How many matches are left for CSK? தூங்க போயிட்டீங்களா எல்லாரும்? Sridhar, can you answer? நீங்க ஒண்ணு எவ்வளவு அப்படின்னு கேட்கிற மாதிரி ஒரு கேள்வி. இந்த கேள்விக்கு நீங்க பதில் சொல்லலைன்னா எல்லாரும் தூங்கிட்டீங்கன்னு அர்த்தம். அப்புறம் நான் எதுக்கு லெக்சர் கொடுக்கணும், எதுக்கு டாக் கொடுக்கணும்? Yes.
Sir, they are hesitant to come, sir. They said answer 2, sir.
Sorry?
They said answer is 2.
Who said? I don't see it in chat.
Uh,
Why can't they write in chat? I'm looking at chat. Okay, so there are 2 matches left. Exactly, correct. Because I mean, இதுல என்ன differential equation solve பண்ணுமா? இது என்ன கேள்வி இது? Okay, there are 2 matches left. So what is the maximum CSK can get? Its current score is 90. There are 2 more matches left. So what is the maximum it can get? Oh, bah. Thank you. $1 million open problem solved. Okay. So maximum CSK gets is 92. Now I am asking, can CSK reach the top? Because on the KKR, RCB, DC, they all have to play. Imagine, try some combinations of the outcomes of these matches, right? There are 3 matches. CSK plays KKR and RCB, 2 matches. It can win. Maximum it can get 92. But there are 3 matches between KKR, RCB, and DC. So, given that, is it possible that everybody will remain 92? Because that's the only way CSK can reach the top. Okay. Now, if you do some calculations, you will realize that no, at least KKR, RCB, DC, Yaraz Wattar will get 93. Okay. Why? It's all some calculations. CSK can get at most 92. For it to stay on top, DC, which is currently 92, should lose its both matches, RCB and KKR. So KKR and RCB will get 92 each by winning against DC. But when they play against each other, one of them is going to win and get 93. Okay. So the answer is no, CSK cannot make it to the top. Here is another argument. Okay. See, math is all about proofs, right? Analytically arguing about it. So here is another argument. Between KKR, RCB, and DC, there are current score is 274, 91 plus 91 plus 92. And there are 3 games left between the 3 teams. So the total, one of them at least will get 277 by 3, which is 93 points. Okay. So here is a simple example, a journalist question who's currently watching the tournament, and he or she has to report saying, here is the current score, here are the remaining matches left. What is the chance? This is not a probability question. This is a deterministic question. Is there any chance for my favorite team to make it to the top, or is it not there? That's all. Okay. So some simple averaging argument can be given. Now, what is the general question? What is the general problem? What is the general question? Because we're not interested in these 4 teams. What is the general proof that if you want to say answer is no? So the general question is, you are n teams, each team playing each other some k times. Let S1, S2, Sn be the current scores. And let Gxy be the number of games remaining between teams X and team Y to be played. Okay, so I give you the current scores, and I give you between team 1 and team 3, there are 3 matches left. Between 3 and 7, 7 matches left. So Gxy is the number of games remaining between teams X and Y. They are to be played. Now my question is, can my favorite team, say team 1, end up in the top? Okay, and we had some argument, some idea of a proof in the previous slide, in the small example. And how do I argue? Let M be the maximum score one can obtain, assuming that one is going to win all the matches which is remaining. Now, here is a claim. My favorite team is eliminated if and only if there exists a subset S of teams such that in that subset, sum of their current scores plus sum of the remaining scores and divide by cardinality of S, which is the average, which happens to be greater than M, then my one is eliminated, right? This is exactly what I argued at the end. Here is this 3 teams, their current score plus whatever is left divided by the number of teams is greater than what the maximum my favorite team can get. Now, one direction is clear, that if there is some subset, we have already argued that you cannot, my favorite team is eliminated, but the converse is very interesting. And again, this whole problem can be modeled using a graph, using source and a terminal and weights on the edges, and using, there is a famous theorem called max flow minimum cut theorem in the area of network flows. Okay, so again, these are some of the very simple, interesting theorems you will learn in graph theory first semester course. Graph theory is an exciting course. As I said, it's a modern number. Graph is equivalent to number. Every numbers of which we have developed a whole lot of mathematics. There is a lot of mathematics developed from graph theory, which is very exciting, current, contemporary. A lot of algorithmic questions can be asked. And what I gave you is just some flavor of a set of questions. Everything can be discussed through tournaments, designing the tournament, the points in the tournament, and so on and so forth. Okay, so let me conclude by saying graphs model a number of interesting relations. In fact, some of these questions, you can ask a lot of these interesting questions and find answers. Some of these questions can lead to open problems, whole research direction that has happened in the world. Okay, so graph theory and algorithms can be taught using tournaments and puzzles, and frame such questions and find their answers. Okay, with that, thank you again. Thank you for the invitation, and thank you for the attention. Thanks. Let me know if you have any questions or comments.
Participants, if you have any questions about this topic, please post in chat box. I think there is no questions. Any questions from participants side?
I have mentioned my
Yeah.
email address in the chat. Feel free to send me mail asking questions, or if you have some answers to any of my questions. Okay, otherwise, thanks again.
So there is no questions, I think.
Okay, thank you.
Okay, sir. Mathematics. I give you a really heartfelt vote of thanks to our speaker, Dr. Venkatesh Raman, who spent his busiest time gracing the occasion. I would like to express our sincere thanks to you for giving excellent coverage to some maths in tournaments. Today, we had the opportunity to hear your ideas in graph theory, and this is definitely encouraging us in our further studies. Your thoughts have enlightened our minds and shows a new path. Thank you once again, sir, for adorning the occasions and sharing your opinions. Thank you.
Okay, thank you. Bye now.
Thank you, sir.